Hello friends. This time I will be discussing about partial differential equation, especially well-known partial differential equations and its applications in engineering. So to start off with, here I will be discussing about one-dimensional heat equation. I have structured this course in such a way that a beginner will be able to appreciate the things whatever I am explaining here with a bit of physical intuition. So I will be trying my level best to make you people understand things or appreciate things physically as well, rather than just a bulk of equations. So without much delay, let me get into the theory. So as we see here, this is a bar, is a one-dimensional bar. Let's say the temperature at this particular point is 100 degrees Celsius and at this point is 30 degrees Celsius. So due to the difference in temperature, we all know there will be definitely a flow of energy from this point to this point. Now actually in heat transfer, what we are interested in is, let's say I'm taking a small area here. I want to know how much energy I'm getting here. The unit of energy is joules. We are interested in the rate at which energy is flowing. So the rate of energy will be watts. So we are interested in the watts. Okay, how much energy, heat energy, is getting transmitted at this particular area. Okay, now let's do a simple thought experiment as I have shown here. Let's say this fellow is doing a cooking. He's doing cooking. Okay, so he's using a metal. In the first case, let's say he's using a metal utensil for cooking. Then he will feel the heat. Definitely he will feel the heat, right? But let's say if you're using the plastic utensil, this particular thing I'm talking about, then he may not feel the heat compared to the case 1, this particular thing being a metal, case 2, this particular thing being a plastic. So in case 1, we know there is more energy getting transmitted to this, getting transferred through this particular area. So let's say so whatever be this energy watts, that is proportional to the material, right? It is proportional, it's not proportional, it depends upon the material what we are using. Okay, now this was the first thought experiment. Now go to the second thought experiment. Again, this particular utensil, let's say the length of this particular utensil is 20 centimeter in this case, in the case 1, in the second thought experiment. In the case 2, let's say I'm using a shorter utensil. In this case, let's say both are made of the same material, let's say metal, copper or any other metal. As we can see here in case 2, he will be feeling the heat very fast, right? So in this case, more amount of heat energy is getting transferred, okay, compared to this particular case. This is a very simple thought experiment. That's why usually we use very long utensils for cooking, not very small ones. Okay, so it is the energy transferred at this particular point depends upon the material, then it is inversely proportional to the distance between these 2 points. Okay, it is inversely proportional to the distance between these points. as we saw in our second thought experiment. Now let's do a third thought experiment, in which, let's say, I'm increasing the temperature at this particular point, or let's say now I'm cooking the food at, let's say, 100 degrees Celsius. So in the third thought experiment, this is the first case, I'm cooking things at a temperature of 100 degrees Celsius. Now case 2 in the third thought experiment is that, let's say I have increased the temperature at which I am cooking to 1000 degrees Celsius. So the first case is 100 degrees Celsius to 30 degrees Celsius. Then the second case is 1000 degrees Celsius to 30 degrees Celsius. So this was the first thought experiment 1, this was the thought experiment 2, and this is our third thought experiment. Okay. So obviously in this particular case 2, energy transferred will be, it will be much, the energy transferred at this particular point in this particular case will be more, because of the very large increase in the temperature. Okay. Now, so from all these three thought experiments, thought experiment 1, thought experiment 2, and then this thought experiment 3, let's say Qx is the amount of energy transferred at this particular point in unit area. The rate at which energy, the rate of energy transferred at this particular point per unit area is directly proportional to, let's say every material has some constant. Okay, it depends upon the type of material, and it is directly proportional to the change in temperature, and then it is inversely proportional to the distance. Okay. Now as we all know, we will bring in some constant, some proportionality constant. Then this equation can be written as k into delta T by dx. Okay. The one thing is, heat will flow in the direction of negative delta T, right? So if delta T is positive, let's say if delta T is positive in this direction, then the heat will flow in the opposite direction. So that means there has to be a negative sign here. Okay. Now in the limit, if in the limit, like as engineers, if limit delta x tends to 0, then this can be written as, this is the rate of heat energy flowing per unit area is equal to k dt by dx minus k dt by dx, where this particular k is called the, if you are a mechanical engineer, it's good for you to know this. Other engineering branches need not bother about this a lot. This is called the thermal conductivity of the material. So obviously, if we go to our first thought experiment, in this case the metal has got a higher thermal conductivity compared to plastic. That's why in this case the rate at which heat was getting transferred to this particular point was much faster. Okay, thanks. So this kind of builds the basics to go ahead and look at the one-dimensional heat equation in a much clearer way.